Hello, friends. It's very difficult to start these live streams, I have to admit. So, today I'm going to walk you through the entire IB structure 2, SL and HL. At least that's the plan. Um, Very questionable decision. Do I have. Okay, let me check. Yes, all working. Yes, very questionable decision because am I ready for this? No. So if you're watching the recording and it's like 9 hours long, I'm sorry, okay, I tried my best. Do I have 120 exams to mark today? Not today, but like in the next 2 weeks? Yes, I do. Could I use this time for paid one-on-one lessons? Yes, I could. And also, guess who failed her driving mock test yesterday and should be practicing parallel parking? You guessed it right. But here I am, and lucky for you, I'm not teaching you business or time management or driving lessons. So I'll be back to my teaching mode in a second. Right. So today, let's see. Yes. So we're going to go through IB chemistry structure 2, SL and HL, ionic model, covalent model, metallic model. And you know how it works. I will show you my lesson slides, and at the top here you would know which part SL or HL this is. So if you're a SL student, you can skip all the HL parts. There would be timestamps, hopefully, if everything works well. There would be timestamps, so you will know what to skip. If you want to say thank you for this video, you know what to do. Share with your friends, subscribe, comment, and there was something else like press like. Yes, that's what it was. All right, well, let's start. So everything is working. Yes, I am live. I just double check. Yes, it's all good. Okay, well, let's start. So structure 2, this is not part of the structure officially, but let's just talk about the types of bonding that we would be covering. So we will be covering ionic bonding, which is happening when you attach through a chemical bond metal and a non-metal, covalent bond when you have two non-metals bonded, and metallic bond when you just have a metal or a metal with another metal. How do you know which substances are metals, non-metals, and so on? You can know it from the periodic table. So this is the periodic table. Periodic table, you know what it is. So if you make an imaginary line like this, yes, so boron, silicon, germanium, arsenic, Sp, what is it, antimony and tellurium. So these are metalloids, and so top right corner would be non-metals, and hydrogen is a non-metal. Everything else is metals. Okay, this periodic table would not be nice and colored in your data booklet, but you have to memorize. I think if you just memorize to draw a line like this, yeah, so the line that splits metals and non-metals, that's how you will figure it out. And this is crucial to finding out. It's very important to understand the bonding type that you have for the substance that you're asked about. Yeah, so this would be the very first step for every question you're solving on bonding, to understand whether it's covalent, ionic, or metallic. Let's do a few examples. So again, that's not exam style, but just to get going. So classify each of the following as ionic, covalent, or metallic. CO2. C is a non-metal. O is a non-metal. Can you see my writing? Um, I hope you can. I hope you can see my writing. Or is my screen frozen? Oh no, I think my screen is frozen. Okay, let's see if that would work. Does that work? It does? Yeah. Yeah. Okay. Yes. So CO2, two nonmetals, which makes it a covalent bond. I'll see if that shows. And then CaS, calcium is a metal, sulfur is a non-metal, so ionic. Then PCl3, P is a non-metal, Cl is a non-metal, so covalent. Iron is a metal, so that would be metallic. And so on. You can do the rest if you want. Everything is showing, right? Yes. Hello, hello. If you tell me you can see my writing, right? If you just message if you can see my writing, that would be great, because I think it should be fine. Now, the type of bonding, whether you get ionic or covalent bond, it would depend on electronegativity difference. So if you have two nonmetals bonded, well, basically, if electronegativity difference is small, which means that you would have two nonmetals which are the same. Yeah, so for example, H and H, H2. So then the bonding pair would be exactly in the middle, because electronegativity is the measure of the tendency of an atom to attract the bonding pair of electrons. So if atom A and B are pulling the bonding pair with equal force to each other, what will happen? Well, the bonding pair would be exactly in the middle, and that is a covalent nonpolar bond. Now, if these two electrons are forming a bond, but atom B is a little more electronegative than atom A, then atom B would attract electron pair closer to itself, which would make it a polar covalent bond. And then if atom B is much more electronegative than atom A, then atom B would take away that electron from atom A completely, and it would form an ion. Yeah, so B becomes B minus, A becomes A plus. So the difference between ionic and covalent bond is that in covalent bond, this pair, it's attracted to both atoms. But in ionic bond, A completely loses its electron, so now you can split them into ions basically. Yeah, so the electron from electron from A is attracted to the nucleus of B. Right. Okay. Next. That's fine. Yeah. So this is covalent nonpolar. This is covalent polar. This is ionic. But we will do it again. Again, this is not officially the part of the structure, so we're just starting structure now. So structure 2.1, ionic bonding. Right. So in ionic bonding, as we just said, electrons are transferred. Yeah. So electrons are transferred from one atom to another. So we would transfer electrons from a metal to a non-metal to form a positive and negative ions. And this is the definition of ionic bonding. Ionic bonding, it's an electrostatic attraction between oppositely charged ions. And by the way, electrostatic attraction, sometimes it's a mark. Yeah, so that could be an entire mark. To just mention electrostatic attraction, then between what and what, that would change based on the type of bonding. So let's say we have sodium and chlorine forming a bond. Sodium is a metal, chlorine is a nonmetal, so electron from the outer shell from sodium would be transferred to chlorine. And what will happen? Well, you would form ions, right? So Na becomes a plus because it's lost an electron. Cl becomes a minus. You see, this is the electron from sodium. So Cl minus, anion and cation. And the attraction between these two oppositely charged ions is the ionic bonding. Right, so just to reiterate what's important, so that's it's electrostatic attraction between oppositely charged ions. If they ask you for a definition and they give you, for example, some specific substance, let's say an ACl, you could say that it's electrostatic attraction between sodium plus and Cl minus. If you are not sure that you won't mess the charges up, the charges must be correct if you mention the ions. You can just say between oppositely charged ions, that gives you a mark. Next, we need to know how to write formulas of ionic compounds. My students love this table. Love this table. So this is the table which has all the names and formulas of all the cations and anions you need to know for IB. This is from the specification for metals. Yeah, so metals are cations. Metals and ammonium are cations, so they are positively charged. You need to know the charges, but for metals, the charges most of the time you can find from the periodic table. For example, if it's if it's group 1, yeah, then the charge would be +1. For group 2, magnesium, for example, it's +2. For group 13, well, aluminium is 3 plus or +3. And then for non-metals, it's not that straightforward. For transition metals, they can have variable oxidation states, right? So we don't know. And for some transition metals, like you need to know the common oxidation numbers. For example, for copper, the common oxidation state, or like charge is 2 plus. For lead, it's 2 plus, could be 4 plus. But for transition metals, they would tell you the oxidation state in the form of Roman numbers. Okay, so you see, for example, copper 2, the Roman number 2, tells you that the charge of the copper is 2 plus. Yep, fine. Fine. You can still see me. Yes, you can. Okay. And for anions, the things are more complicated, especially considering that some anions are polyatomic. So polyatomic anions you definitely have to memorize. So for example, OH, you need to know that OH minus, it's a hydroxide. You need to know that the charge is -1. NO3 is nitrate, the charge is -1, and so on. Yes, so all of these with the charges you have to know. Then also for binary compounds, if you have halides, well, for halides you could memorize them if that makes it easier, yeah, but you can also figure them out from the periodic table. So if the compound is binary, which means that it's formed only from a metal, one metal and one non-metal, you can find out the charge of the non-metal by the number of the group. So for example, you see oxygen, it's in group 16, which means that it has 6 valence electrons, which means that it's missing 2, which means that it would gain 2 from a metal and it would become 2 minus, right? So you're just counting kind of how many electrons are missing from the complete octet, yeah, so from 8. For example, nitrogen would form 3 minus because it has 5 valence electrons, so it needs 3 to make an 8. Okay, I hope that's fine. But again, if you don't like this method, just memorize them from the table. A word of warning about names: bromide, chloride, fluoride. If instead of bromide you say bromine, you lose a mark, because when you say bromine, you mean Br2. Bromide, it's Br minus. Yeah, so be very careful with the endings. Nitrate, it's NO3 minus. If you say nitrite or something, you lose a mark. Yeah, so these have to be very specific. Sulfate, SO4 2 minus. And now let's assume you've memorized those. Done. Memorized. What do we do next? Next, we need to know how to use this table to write down formulas of ionic compounds. Well, let's do it using the example. So for example, let's write the formula for lithium bromide. What do we do? Well, we find lithium. There it is, Li plus. And we find bromide, Br minus. 1. Yeah, plus and minus means +1 -1. Then what do we do? We crisscross the charges. So not charges, but the numbers. Yeah, so the charges, like, you don't really care what's the plus, what's the minus, but what you care about is that it's +1 and -1. So 1 goes to lithium, 1 goes to Br. Yeah, so we're crisscrossing. So the formula for lithium bromide is LiBr. Pretty straightforward when it's 1 and 1. Now let's try magnesium chloride. Okay, magnesium chloride. So magnesium, it's 2 plus. Where is it? 2 plus. I don't even have magnesium. Yeah, no, I do have magnesium and chloride Cl minus. Yeah, from the table again. Cl minus. Cl minus again, like 1 minus. So 1 goes to magnesium, 2 goes to chlorine. The 1 you don't have to write, obviously. So that's MgCl2. Yeah, we're crisscrossing stuff. Let's try calcium hydroxide. Calcium 2 plus calcium 2 plus hydroxide OH 1 minus. 1 minus, what do we do? Crisscross. 1 goes here, 2 goes there. So it's calcium 1. OH, it's a polyatomic, right? So you have to show that the 2 is referring to the entire OH thing. That's why I put it into the brackets. OH2. Okay, you can message me in the chat, by the way. If something is not clear, just let me know. I'll explain again. Let's do ammonium sulfate. This one, ammonium. Too many. Okay, ammonium sulfate. Ammonium is NH4 plus. This is our guy. Sulfate, SO4 2 minus. The entire SO4 has a 2 minus charge, right? So 2 goes to NH4, 1 goes to SO4. And again, NH4 plus is like polyatomic, many atoms. So I have to put the brackets. NH4 2 SO4. Good. I hope it's fine. Next. Next, let's talk about the structure of ionic substances. So whenever you have an ionic substance, it would have a giant ionic lattice. And so the only type of structure possible for ionic substances is a giant ionic lattice. How does it work? So in a giant ionic lattice, you have positive and negative ions, and they would be arranged not like molecules. Yes, so you would not, for example, you have an ACl, you would not have a molecule of an ACl here, a molecule of an ACl there. That's not molecular. And what you would have is, you would see, if you were to zoom in, yeah, and look at it under the microscope, you would see that cations and anions are arranged in a huge lattice. So if you have a crystal of sodium chloride, well, essentially just like one huge ionic lattice, where sodium plus ions would be like interchanging with Cl minus. Yes, you have Cl minus, Na plus. That's how it looks, obviously without any lines, yeah, without the black lines. And this is a cubic lattice. You see it forms like a little bit of a cube there. Also, I don't know if you need to know that in this new syllabus, but in the previous syllabus you needed to know that it's 6 by 6 lattice, so it means that each sodium plus ion was surrounded by 6 Cl minus ions. Now about the properties of giant ionic structures. So giant ionic structures, they have lattices, they have high melting and boiling points. Why? Because if you were to melt or boil it, you'd have to break electrostatic attraction between Na plus and Cl minus, yeah, which is very strong. So electrostatic attraction between oppositely charged ions is strong. They have low volatility, which means that it's not easy to evaporate, and that's kind of logical if you think about a sodium chloride. Well, it's table salt. Yes, think about table salt. Can you evaporate it? Well, not really. Yeah, not really. So it's not volatile. It's often soluble in water, not always. Some ionic substances would be soluble, some not, but they could be soluble. This is very important. This part, it's asked about, like they always ask about that. So ionic structures, ionic lattices, ionic substances, they don't conduct electricity when solid. Why? Because for electrical conductivity, what do we need? We need mobile charged particles, right? Do we have charged particles here? Yes, it's Na plus and Cl minus. Are they mobile in solid state? No. Why not? Because they are held in the lattice. Like, how would they break free? We just said that it takes a lot of energy to break the lattice. Okay. Will this be included in the formula unit mass? Uh, what exactly? You mean, if you mean the small numbers, like the coefficients, not coefficients, but like these small numbers that I showed? Yes, if you calculate the relative formula mass, then you have to calculate, for example, for calcium hydroxide, it would be 1 calcium plus 2 oxygens plus 2 hydrogens, if that was your question. If you meant something else, then ask again. Okay. So no conductivity when solid, but they would conduct electricity in molten or dissolved state, because if they're molten or aqueous, then ions can move. Yeah, so you have charged particles and they are mobile. And this is the Mark scheme explanation for melting point and for volatility. Again, for Mark scheme explanations, be very careful with wording, because now I'm marking exams and I can see the pattern. Like, I can see some really weird word collocations which are not accepted in the mark schemes. So just learn it right from the beginning. If they want you to use the word electrostatic forces of attraction, we'll use it. Yeah, don't just say attraction, say electrostatic attraction. Just use the things examiners are looking for, because it's not like when we mark, it's not like we just look at the entire meaning. We have to spot certain words. Yeah, if I don't see the word electrostatic, I'm not allowed to give a mark, even if what you mean is exactly the same what's in the mark scheme. You have to use specific words. All right, so explanation for high melting and boiling point is that ionic substances have high melting and boiling point and low volatility because of strong electrostatic forces of attraction between oppositely charged ions, which require a lot of heat energy to break. Fine. And also, the higher the ionic charge and the smaller the radius, the higher the melting and boiling point would be. Yeah. So high high charge, small radius results in a stronger attraction, so higher melting and boiling point. Now again, the Mark scheme explanation for electrical conductivity. Ionic substances do not conduct electricity when solid because ions are held in the lattice. And you should not say any other word for the word lattice. It is a lattice, okay? It's a giant ionic lattice. And you're welcome. And if so if for example, like just now I was marking a paper, and instead of saying giant metallic lattice, they said something like just metallic lattice, or like this word lattice is very important. Okay, if you use some other word, I don't even remember, but students are they can use various words instead of that. You need to use the word giant lattice or just lattice. Yeah. So Okay, so don't conduct electricity when solid because ions are held in the lattice, and ionic substances conduct electricity when molten or in the solution because ions are free to move and carry charge. Fine? I hope that's fine. There is a little bit of a lag, so I'm asking questions, but then I know you might answer a bit later. Just let me know if everything is clear. Then lattice enthalpy. Oh, we would talk about that a lot, yeah, but not yet. Not yet. It would be coming later, not today. Lucky for you, not today. So lattice enthalpy. It's the enthalpy or energy change when 1 mole of a solid ionic crystal is broken into scattered gaseous ions, whatever that is. Just for now, we would talk about this in details. And then let's just, so lattice enthalpy for now, we needed to use as a measure of the strength of ionic bond. Yeah, so lattice enthalpy can be used to measure the strength of ionic bond. So basically, the higher the lattice enthalpy, the stronger the ionic bond. Yeah, because lattice enthalpy shows how much energy you need to supply to break apart the ions. And again, the higher the charge and the smaller the radius, the greater the lattice enthalpy. But we would talk about this when we do HL reactivity something. So that's when Born-Haber cycles are. Okay, guys, that's it. We've done ionic lattice and it took us just 20 minutes. Okay, there is hope. There is hope. Let me read the chat for a second. So that I answered, and then can you please explain Gay-Lussac's law for gaseous volumes? Not today, okay? I think what you could do is you could just send me a message with all. So if you want me to explain a specific topic, leave a comment because I will not see the chat. So if you could leave comments or maybe send me a message so that I see which topics are requested, and then I'll make a separate live stream on the requested topics, okay? This would be about structure 2. I forgot which structure we're talking about. All right, so structure 2 SL. Yes, so again, SL part, covalent model. So for ionic model, there was no HL part, everything was SL. Now we're talking about covalent model. I hope everyone's ready. This would be a longer one. Yes, so that's the longest part of the topic. And it would have SL and HL parts. So, definition. Covalent bonding is electrostatic attraction between the shared pair of electrons and the nuclei of atoms making up a bond. Okay? See the difference? There, electrons were transferred. Here, electrons are shared. What does sharing mean? It means that they're attracted to both nuclei. So they form a pair, and that pair is attracted to both nuclei. Fine. Again, definitions, very specific for IB, you have to know that. Yes, so electrostatic attraction between what and what, that's what's changing. Shared pair of electrons and nuclei of atoms making up the bond. And now everyone's favorite part, everyone's favorite, Lewis structures. Lewis structures, what do they show? Well, Lewis structures essentially they show how the covalent bonds are arranged between atoms, and also they show lone pairs of electrons everywhere. Yeah, well, everywhere, but in the outer shells, obviously. So, let's see. I will explain my own method how to draw Lewis structures for IB chemistry and for A level. If you're for some reason are A level and watching this, that would work for A level as well. Right. Let's see. So I'll just walk you through the method and then I'll show it using an example. So first step would be to identify the central atom. So for example, let me actually do this using a CO2 example. Let me zoom out a little bit. Yes, so okay, first thing that I would do is I would identify the central atom. So let's say you have a CO2 molecule. What is the central atom? Well, central atom, there are different ways to figure it out, but my way is to just the atom that's on its own. So there is one C, let it two oxygen, so C is the central atom, C. Calculate the total number of valence electron pairs. Just let it just read it again. Calculate the total number of valence electron pairs. Valence, it's outer shell, yeah, in the entire molecule. And remember, we're talking about covalent substances. Never do this for ionic, yeah? For ionic, we don't do Lewis structures, only covalent. Right, so for CO2, how many valence electrons does carbon have? It's in group 14, so 4. 4 outer electrons for carbon. And then we have 2 times 2 oxygen, so 2 times oxygen is 6, yeah, because group 16 times 6. In total, it's 4 plus 12 is what? 4 plus 12 is 16. electrons, right? Yes. No calculator. I can do this. 16 electrons, and if I convert it to pairs, it would be 8 pairs. Yeah, or 1 pair is 2 electrons. 8 pairs. You don't have to convert to pairs. I like converting to pairs because then numbers are slightly, more manageable for a biologist brain. 8 pairs. Then that was step 2. Connect all atoms to the central atom with single bonds. One single bond is 1 electron pair. So I connect all oxygens with single bonds. Next step, assign lone pairs on the side atoms so that the octet for pairs is achieved on the side atoms. Okay, octet is 4 pairs, so by default all our side atoms must have 4 pairs. So this oxygen has 1. It means that it's missing 3 pairs. I would write down lone pairs as line. Yes, so each line is a pair. So 1, 2, 3. You see now it has an octet. Now it has 8. 1, 2, 3, 4. Now next oxygen, well, same thing. It has 1 pair. It's missing 3 more pairs. So I have assigned lone pairs to the side atoms. Next step. Step 5. If there are electron pairs left, assign them to the central atom. So at this stage, I'm counting the number of pairs I have used up out of 8. So how many pairs have I used up? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 8 have been used up. So which means that there are no lone pairs on carbon. I don't have any pairs left. And the final step is, if the central atom does not have an octet, so has less than 4 electron pairs, move lone pairs from the side atoms to form double bonds. That's what I'm checking now. So I check that my carbon, it doesn't have an octet, it only has 1, 2 pairs, which means that I have to form double bonds. So it's missing 2 pairs, so I form double bonds. To form double bonds, what I will do, let me put it here, I will remove 1 lone pair from 1 oxygen, for example this one, and make it a double bond, and then I will remove a lone pair from another oxygen and make it a double bond. Now everyone is happy. I haven't violated the octet rule, and carbon has an octet and side atoms have an octet. Okay, this needs to be practiced, of course, right? It's not like you would learn how to do it after one lesson. So you have to practice, but I will show more examples. Let's do PCl3 using the same method. So my central atom is P. Then I calculate the total number of valence electron pairs. So phosphorus. Phosphorus is group 15, there it is. So it has 5 valence electrons plus 3 times Cl. Cl is in group 17, so it has 7 valence electrons. And in total, that is 21 plus 5. What is it? 21, 26 electrons, or 13 pairs. Then I connect side atoms to the central atom with single bonds. So chlorines are side atoms. I connect them with single bonds. That was my step 3. Yeah. Then I would assign lone pairs to the side atoms. Each chlorine is like it has 1 bond. Yeah, so each chlorine has 1 bond. So each chlorine is missing 3 bonds. 1, 2, 3, 1, 2, 3. Then I count how many pairs out of 13 I have used up. I have used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 13, which means that the 13th pair would be a lone pair on phosphorus. There it is. And do we need double bonds? So the last step is I check if the central atom has an octet. Well, phosphorus has an octet already. Yeah, so it has 1, 2, 3, 4 bonds, which means that I don't have to form any double bonds. Fine. Okay, now I will do NO3 minus on another slide so that you don't see the steps. Yeah, let's see if that would work for us. Let's do it for NO3 minus. By the way, what is the minus? The minus just means that you have to add 1 electron, 1 extra. Yeah, right. Nitrogen is the central atom. Now I'm counting the valence electrons. Nitrogen is group 15, so 5 electrons in the outer shell, so 5 plus 3 times 3 oxygens. 3 times oxygen is 16, so 6, and 1 more because it's minus 1. Yeah, so plus 1, and that is 24, and that's 12 pairs. Yeah. Then I connect oxygens with single bonds. 1, 2, 3. Then I assign octets on oxygens. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, so that they have 4 pairs. And then I count how many pairs out of 12 I have used up. I have used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 12. What does it mean? It means there are no lone pairs on nitrogen. But is nitrogen happy? It is not, because it has 1, 2, 3 bonds and it wants to have 4, which means that it's missing one bond, which means that I can remove one lone pair from any oxygen and make it a double bond. For example, I can remove this one, make it a double bond. That's milieu structure, and you miss a mark here if you don't put the minus. So then I put the square brackets and put the minus. That is my correct milieu structure for NO3 minus, for nitrate ion. Good, good. Okay. Any questions should be sent to the chat. Right. But there are exceptions, right? Exceptions. Hydrogen can have a maximum of one pair. So you never put octets on hydrogen. Yeah, so it can only form one bond because it's there it is. Yeah, so it is 1s1, so it only has place for one other electron, so it forms one bond. Beryllium forms 2 pairs. A boron is stable with 3 pairs, although could form 4. And period 3 elements and below they can have, but for IB, like, you never have below period 3, I think. So they can have up to 9 pairs. So this is called an expanded or extended octet. Yeah, so when, for example, phosphorus or sulfur or chlorine or bromine, they don't necessarily have to have an octet. They can have more than 4 pairs, and they're fine because they have the 3D sublevel. Explanation you don't need to know. Well, let's just go over these quickly. So water, I would do everything normally, yeah, but just remember that hydrogen is an exception. So oxygen is my central atom, then I'm counting the number of valence electrons. So it's 2 times 1, hydrogen is 1, yeah, plus oxygen is 6. So it is 8 electrons or 4 pairs. Then I connect hydrogens with single bonds. And then that's where the exceptions comes into place. I don't put octets on hydrogens, so I just leave them. And then I count the number of pairs out of 4 I have used up. So I have used up 1, 2, which means that oxygen has 2 lone pairs. And oxygen is an octet. Obviously, hydrogen cannot form double bonds, so I don't even have to check the double bonds actually. Now BF3. Boron is the central atom. Let's count the number of valence electrons. Boron, group 13, so 3 valence. Fluorine, group 17, so 7 valence electrons. So it becomes 3 plus 3 is for boron, then 3 times 7, that's fluorine. So what do we have? 21 plus 3, 24 electrons or 12 pairs. Then I connect side atoms with single bonds. Then I assign octets on fluorine. Fluorine has octets, right? Normal side atom, not hydrogen, so octets on fluorine. Then I count the number of pairs I have used up out of 12. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 12 are used up, which means that boron does not have a lone pair. But boron is an exception, doesn't need an octet, stable with 3 pairs, so I leave it like that, okay? You see boron 3 pairs, it's fine, it's okay. You don't need the double bonds here. You cannot have double bonds here, you will be marked off. Good? Good, good. Okay, I think it's fine. And last one, let's do PCl5. Okay, phosphorus. We already saw it. It has 5. Oh no, that's my marking. Oh, which I'm not supposed to show you. Okay, so that's 5 for phosphorus. Where is it? There. Yeah, so 5 valence electrons. And what was it? Chlorine. Chlorine has 7 because it's in group 17. So 5 plus 5 chlorines. 5 times, I'll just do it this way, 7. So that is what? Who knows, who does mental math well? So 5 plus, oh, what is it? 5 plus 35. Oh my god, that is 5 plus 35, 40. 40 electrons or 20 pairs. I put phosphorus in the middle. That's the central atom connected to chlorines. Cl, Cl, Cl5 chlorines. Then I put octets on the chlorines. Then I count how many electron pairs out of 20 I have used up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There is a faster way to do it. Yeah, 20. But the point is, I have used up 20 out of 20. What does it mean? It means there are no lone pairs on phosphorus. But if you check phosphorus, now that I have to check whether it's an octet, well, it's more than an octet. It's 1, 2, 3, 4, 5. 5 pairs. Is it okay? For phosphorus, yes, it is okay. Why? Because you see it's it's period 3, which means that it has 3D, which means, well, empty 3D, yeah, which means that it can have more than 4 electron pairs around it. And for example, NCl5 does not exist because nitrogen cannot have more than an octet, since it only, like, its outer shell is the second shell, and the second shell doesn't have the 3D or 2D, yeah, for that matter. So nitrogen can only have an octet, and that's the reason why nitrogen NCl5 does not exist. Yeah, nitrogen pentachloride or whatever that is. Right. Okay, so we went through exceptions. Next would be single, double, and triple bonds. Well, this is very easy. So you already saw that sometimes we can have single bonds, sometimes we have to put double bonds, as was the case for CO2. And the double, triple, and single bonds, they differ in strength and in length. So the strength of the bonds: single is the weakest, triple is the strongest. Why? That's actually a new explanation for the new syllabus. So single bonds are weaker than triple because single bonds have one shared electron pair as opposed to 3 pairs in triple bonds, and so electrostatic attraction between shared electrons and nuclei is weaker in a single bond. So you always have to refer back to electrostatic attraction, right? And never contradict yourself. If you say, so electrostatic attraction between, for example, ions is weaker, you lose all the marks. That's a contradiction. Examiners' favorite part, because you never know whether to ignore it or mark you off. But usually we mark off, so just for you just for your information, okay? So do not contradict yourself. If you're talking about covalent bonds, it's attraction between shared pair of electrons in the nuclei. Now the length. For the length, well, guess what? Yeah, the single bonds are the longest, triple bonds are the shortest. Why? Because, again, same explanation. Single bonds are longer because they have one shared electron pair between the nuclei, yeah, and which are attracted to the nuclei. So the electrostatic attraction between the shared electrons and nuclei are weaker in single bonds. So the distance between the nuclei would be larger. Yeah, very straightforward, I think. Next, structure 2.2.3. That's actually all SL, yeah? It's still SL content. A dative covalent bond or coordinate bond. It is a covalent bond in which both electrons come from the same atom. And let me explain this. So let's say you have NH3. Yeah, let's put NH3 as an example. I mean, for Lewis structure, we don't draw dot and cross diagrams. Yeah, that's too complicated, takes too long. So I would not draw dot and cross diagrams if I were to, for example, asked to show the Lewis structure. But for covalent bonding, like if you want to understand whether the bond has, like whether there is covalent bonding, is it dative or normal, you have to draw a dot and cross diagram. So let's think about NH3. So in NH3, well, there are 3 normal bonds. What do I mean by normal? By normal covalent, when I say normal covalent bond, that's not an official term, but I just mean that so one electron comes from nitrogen, one electron comes from hydrogen, they form a pair, and that pair is shared between the nuclei, like is attracted to both nuclei, yes, it's shared between the atoms. Now nitrogen has a lone pair. Yeah, this is a lone pair, lone pair or non-bonding pair of electrons. There it is. So these bonds are just called covalent bonds. Fine. But then you see nitrogen has this lone pair. It can form a bond with something that can accommodate that lone pair. So for example, you know how hydrogen atom, it's hydrogen with an electron. If hydrogen loses that, that's not the best place to draw it. There, yeah, hydrogen with an electron. If hydrogen loses that electron, it becomes H plus. And what does it have? It has an empty orbital. H plus has an empty orbital. And now, if they react, if H plus gives the orbital, nitrogen gives its lone pair, they form a covalent bond, but it's not a regular covalent bond. That's the dative covalent bond because, or coordinate covalent bond, because both electrons here are coming from nitrogen. That's the only difference. If you were to study, for example, the properties of that bond, or if you were somehow able to see it under a microscope, which you can't, but if you could, you would not see any difference. Yeah. The only difference is that both electrons are coming from nitrogen. Well, that's your dative covalent bond. And again, to figure it out, whether the substance has dative bonds or not, I think you do need to draw dot and cross diagrams to really track every single electron, which is very time consuming, and it's only 1 mark in paper 1. I don't think it's worth it, to be honest. But depends. If you're aiming at a 7, maybe it is worth it. But if not, then up to you. Okay, I'm not giving advice to skip some topics. I'm not for the record, yeah. But I think you should memorize these ones. So you should just memorize that typical substances that are asked about. So NH4 plus has a dative bond, H3O plus has a dative bond, and CO, the unexpected one, they ask about it all the time. Yeah, so in multiple choice questions, usually you would see these ones. Yeah, I think in the specimen paper there was something else. There was some weird like NO3 something, NO something, but these are the ones that are most commonly asked. Okay, dative bond done. Next bit, it's the HL part. So SL students can have a break, or you can skip to the next bit. Not done during the live lesson though. If you are watching the recording, you're lucky. If not, you have to just have a break if you're an SL student. Right, this is an HL content transition metals complexes. So, definitions. Transition metals are elements that form at least one stable ion with partially filled d subshell. Form at least one stable ion with partially filled d subshell. Guess what is the most common mistake? And in A level, that mistake sometimes costs 6 marks. In a level of response question, yes, we had a lot of answers with their own definition, and if you don't know the definition, you do everything else wrong. So the element must form an ion with a partially filled d subshell, not an atom. So if an atom has an incomplete d subshell, it does not automatically mean that it's a transition metal. Yeah, right. Okay. And for that reason, scandium and zinc are not considered transition metals, because if we write down the electron configuration, for example, for scandium it would be argon 4s2 3d1, for zinc argon 4s2 3d10. So scandium forms the only stable ion, which is 3 plus. And remember in structure 1, in that very long live stream, we talked about how to figure out the a configuration for ions, yeah. So we remember that 4s electrons are removed before 3d. So scandium 3 plus, for scandium 3 plus you remove 4s2 and 3d1. So scandium 3 plus has 0 electrons in the d sublevel, so it does not form an ion with partially filled subshell. That's why it's not a transition metal. Zinc, if you make an ion, the only ion it can form is zinc 2 plus. Remove 4s, 3d10 is left. 3d10 is fully filled, so not a transition metal. And then random facts about transition metals. I am just following the syllabus. Transition metals exhibit more than one oxidation state, form complex ions, form colored complexes, often act as catalysts, and exhibit magnetic properties. Then what is a complex ion? Complex ion is a central transition metal ion surrounded by ligands. So for example, this is a complex ion. What do we have here? Well, we have cobalt in the middle. That's a transition metal ion, and it is surrounded by NH3, which are ligands. Ligands are negative ions or neutral molecules which use a lone pair of electrons to bond to a transition metal ion to form a complex ion. This is really confusing, I understand, because you have a complex, like you have a cobalt in the middle, which is a metal ion. And what does nitrogen do? It forms a dative covalent bond. Okay, just accept that. Yeah, that's a fact. Dative covalent bond is formed from the ligand to transition metal ion. What's important when you are asked to draw the transition, to draw the complex ion, you write down the transition metal in the middle, and then the ligands must be written in such a way so that you draw the line, the bond, from the metal to the atom that donates a lone pair. Okay, so the bond must go from the lone pair essentially to the transition metal ion. If, for example, you write it down like this, so instead of writing NH3 like that, you would write it as NH3. You lose a mark because then it would look like your cobalt is bonded to hydrogen, and everyone is very picky about it. Yeah, so don't do it like that. So identify the atom in a ligand that has a lone pair, and then draw a bond directly to that ligand. Yeah, to that atom. For example, for CuCl4, it's not 2 plus, it's 2 minus though. Yeah, there's a typo. 2 minus. Why is it 2 minus? Why is it 2 minus? Because copper is 2 plus, each Cl is 1 minus, so overall charge is 2 minus, 2 plus, minus 1 minus 1 minus 1 minus 1, which gives you 2 minus. Yeah, again, well, here it's very straightforward. You have copper bonded to chlorine. Chlorine donates a lone pair. With platinum, again, you see I'm not writing NH3 like this because this is wrong. Yeah, so it would look like H is donating the lone pair, which it doesn't. And these are fine. Yeah. So typical ligands would be chlorides, NH3, water. From oxygen there is a lone pair. Yes, okay. This was it for the complex ion part. If you think that's all, you are wrong. We will go back to ligands also in some other structure, or no, we'd go back to this in reactivity. So we will get back to that. I don't know why it's here in this structure. I'm following the IB syllabus. The next bit. Okay, the next bit is both SL and HL. The first part is SL, but then I'll tell you this table, it's for both SL and HL students, but I'll tell you where to stop, which is the threshold for SL. So the next bit we are talking about is valence shell electron pair repulsion theory, which is VSEPR or something, SEPR. So what does it tell us? So this theory, it tells us how to predict the shape of the molecule based on certain assumptions that we're going to make. What are these assumptions? The first assumption is that electron domains in the valence shell of the central atom in the molecule repel each other, taking positions to minimize repulsions. What does it mean? So you have the central atom. That central atom has a ton of electron domains around it. Electron domains just like a region of high electron density. Could be a bonding pair, could be a lone pair. So it has electron domains around it. Yeah, so that's like the lines that we drew when we did Lewis structures. Now these electron domains repel. Why wouldn't they repel? They're negative, they repel. All good. Yeah, so electron domains in the valence shell of the central atom repel to take positions to minimize that repulsion. And the repulsion is not equal. Lone pairs repel more than bonding pairs. So lone pair repulsion is the strongest. Bond pair repulsion is the weakest. Because if the repulsion was the same, we would always have the same bond angles depending on just how many bonding pairs we have. But that's not true. Yeah. So this part you need to know for both SL and HL. Now the table. Now we will use this table to identify the shapes of the molecules. Again, everyone's favorite table. Another table. This structure 2 is full of tables, and everyone has these tables printed out and put on to the mirrors and everywhere. Yeah, so my students have these tables everywhere, and they say that they feel attached and they don't even take them off when they're in the university, so that's nice. You can also print them out. If you need the notes, you can ask me, I'll send you the notes. So table. With this table we will be identifying the shapes of the molecules. How does it work? So to find out the shape of the molecule, what do? We need to draw the Lewis structure, just how I explained. Yeah, we practiced that. From the Lewis structure, what would we know? We would know the number of atoms bonded to the central atom, the number of lone pairs, and then you just pick the correct line. So if we had, for example, two two atoms bonded to the central atom, and two lone pairs. The shape would be bent, the bond angle would be that, and electron domain geometry would be tetrahedral. I'll explain the difference between actual shape and electron domain geometry in a second. But you understand how to use the table, right? So you draw the U structure, find the number of atoms bonded to the central atom, find the number of lone pairs on the central atom, and then that's your actual shape, that's your bond angle. Let's talk about bond angles a little bit. So you see what's happening here. So let's say you have a tetrahedral structure. Yeah, tetrahedral structure. Well, I don't know. I mean, I know it's like that. Yeah, just a small tetrahedron. Tetrahedral structure. It's four atoms bonded to the central atom, zero lone pairs. The bond angle is 109.5. So that bond angle, it just happens when you have equal repulsion between bonded pairs. That's it. You get just arrange four electron domains with equal repulsion. Somehow they would arrange at 109.5 degrees. Now, if you substitute one bonding pair to a lone pair, what would we get? We would get 3 bonding pairs, bonding domains, yeah, because double bond is also like bonding domain. So I just count the number of atoms basically. So if it becomes 3 1, then the lone pair has an extra repulsion. So each lone pair would decrease the bond angle by approximately 2 to 2.5. So instead of 109.5, I end up with 107. You see that minus 2.5 or 2, something like that. 107. Now what happens if you substitute another bonding pair by a lone pair? So now we end up with 2, 2. And then you subtract 2.5 again, so it becomes 105 or 104.5 predicted bond angle. You see, how can you figure it out? And for all of these, the electron domain geometry is tetrahedral. So what is the electron domain geometry? So electron domain geometry, it doesn't distinguish between bonding pairs and lone pairs. So essentially, if you could see the lone pairs, what geometry would you have? Yeah, so actual shape, you just see atoms, you don't see electron pairs. But in electron domain geometry, which you cannot see, yeah, there it is, you can see also the lone pairs. So if you have 4 electron domains, you have 4 0 or 4 in total, or 2 plus 2 is 4, or 3 plus 1, you see all of those would give you tetrahedral arrangement. I hope that makes sense. And the same logic works for everything else. So for example, if you have 3 0, that's trigonal planar, yes? So if you just have 3 bonding pairs with equal repulsion, they would end up at a bond angle of 120. Now if you substitute one bonding pair to a lone pair, so you end up with 2 1. So you see the bond angle becomes 120 minus like 2 to 3, yeah, 117. And again, the bond angles, you don't have to memorize them exactly. There is always a range that they accept, and the true bond angles would slightly be different anyways. But yeah, they accept the range. But the trend is there, right? So if you just understand the trend, so how you substitute bonding pairs with lone pairs and what happens to bond angle, that would make your life much, much easier. If you do not like my explanation, that's fine. You just have to memorize the table then. Yeah, so you can also just learn the whole table with shapes, with bond angles, and with electron domain geometry. That's also fine. Now, for SL students, you need to know this table up to 4 electron domains, yes, so up to this part. So this part is for SL students. So you need to know linear, V-shaped, trigonal planar, trigonal pyramidal, and tetrahedral. For HL students, you need to know also up to 5 and 6 electron domains. Yeah, so the rest of the table you also need to know. Well, let's do a couple of examples, yeah? Let's do a couple of examples. These are the shapes. I will not even I think I won't stop on the, yeah, you can screenshot and have a look if you want, but I think it's fine. The shapes, I'm not going to visualize them. So let's predict shapes and the bond angles for the following molecules. We are 55 minutes in. Okay, not bad. Xenon F4, by the way, xenon, it's what? It's a noble gas. Surprise, yeah, surprise. Remember how we learned that noble gases don't form bonds? Well, guess what? Life will never be the same again. Xenon F4. So xenon has 8 electrons in the outer. So I started by drawing the Lewis structure, right? Because I have to find out the number of lone pairs on xenon to find out what the shape is. So xenon has 8 electrons in the outer shell because it's in group 18. Fluorine has 7 electrons. You cannot see it, but trust me, yeah. Okay, so xenon has 8, fluorine has 4 times 7. 8 plus 4 times 7 is 36 electrons, or 18, yeah, or 18 pairs. I put xenon in the middle, attach fluorines with single bonds the side atoms, then I place octets on the side atoms. 3 fluorine needs 3 pairs each. I hope you understand what I'm doing because I explained it in the beginning, and you can just move back to Lewis structures if you don't understand that. Right, and then what do we do? Then we find out how many pairs out of 18 I have used up. I have used up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 out of 18 are used up, which means that there are 2 lone pairs on xenon. And it's fine, it doesn't need double bonds, it's already more than an octet, right? So it already has 1, 2, 3, 4, 5, 6. All good. Now let's look at its shape. So I go to the table. It has 4 atoms bonded to the central atom and 2 lone pairs. 4 atoms bonded to the central atom, 2 lone pairs, gives me a square planar shape, bond angle 90 degrees. Yeah, that's it. That's how you use the table. But careful, what do they ask? Did they ask for actual shape or electron domain geometry? Well, electron domain geometry would be octahedral, but they didn't ask about that, so that's what I write. So that's square planar. And the shape names, you need to know how they are in the syllabus, right? So don't invent your own shape names. Planar 90 degrees bond angle. Fine, let's do one more for S. I don't have anything for SL though. Well, okay, let's do maybe SF6. SF6. Or I should do one for SL though. After this one. Okay, let's do SF6. So sulfur has 60, like it's in group 16, so it's 6 electrons in the outer shell plus 6 fluorine. So 6 times 7 fluorine I already memorized, which is 48, is it? It is, yeah, 48 electrons or 24 pairs. And then I put sulfur in the middle, then attach fluorines with single bonds. Then I put octets on the side atoms. Then I count how many pairs out of 24 I have used up. I have used up 1, 2, 3 times 6 plus 1, 2, 3, 4, 5, 6. I have used up 24 out of 24, which means that sulfur has no lone pairs, and it's more than an octet already. Yeah, that has an expanded octet, so we don't do anything with in terms of double bonds. Then I go to the table, so it has 1, 2, 3, 4, 5, 6 atoms bonded to the central atom, 0 lone pairs. 6 atoms bonded to the central atom, 0 lone pairs is octahedral shape, and 90, well, 90, and I think sometimes they put 180 degrees. I don't remember how it is in the new spec, that one I'd have to double check, yeah, but in any case, you know what's octahedral shape, so it's octahedral with 90, I would say 180 degrees and 180 degrees just in case, but you know what's octahedral, right? So you have sulfur as the central atom, and then the rest of the atoms are arranged like that. So basically you go an atom here, atom there, atom there, and atom there. That's in the plane, yeah, and then one on top, one on the bottom. So basically you have 90 degrees between these guys and then 180 between the top and bottom one. But again, no one asks you to visualize. They might ask you to draw them in 3D, but only some structures. Let's just do that for some, just in case. So if the structure is what was it, tetrahedral? No, yeah, let's do tetrahedral first. So if it's tetrahedral, and then if in an unlikely event they would ask you to draw the 3D structure, which is very rare, I've seen it like once maybe, then you draw it like that. So let's say you have carbon, like some central atom, and then you do two normal bonds, one dashed and one bold. What does that mean? The normal bonds are in the plane of your paper. The dashed one goes, like, this is the plane of your paper. The dashed one goes below. The bold one goes above. Yeah, that's tetrahedral structure. If the structure is octahedral, you can draw in different ways. For example, you can draw like that. You can draw these two dashed, these two bold, and these two normal. Yeah, that works for octahedral structure. And if it's trigonal pyramidal, let's do that as well. So if it's trigonal pyramidal, then you would have normal. It's like a tripod, dashed and bold. Again, like, you don't, very unlikely they would ask you. Usually this guy would have a lone pair. Yeah, but just in case, if they ask you to draw something in 3D, then it would be one of these. Now you know. Now you know it can get that extra mark. Right. Well, yes, I think it's fine. I think if SL students just use this as the practice for the shapes, nothing wrong will happen. Your brain would not explode, okay? That's just a couple of more electron domains. Just make sure you don't memorize this part of the table. If you do, just don't occupy that extra space. You'll need it for something else. Right. Next part. Next part is bond polarity. Okay, so we're halfway through and we are 1 hour in. All right. Bond polarity. So a difference in electronegativity in a covalent bond leads to a bond polarity. And you have to be very careful with the questions. They might ask you about polarity of bonds or polarity of molecules. I'm now talking about bond polarity. Okay, so the bond within molecule may be polar. That's SL, by the way. So if you have two atoms, non-metals, we're only talking about covalent bonds, with different electronegativity, then the molecule would be polar because I mean, not molecule, the bond would be polar because there would be a dipole moment between the two atoms. So the dipole moment is the measure that describes two opposite charges separated by distance. So if you have an HCl bond, the more electronegative atom is chlorine. How do you know that? Well, from the periodic table, you have also in the data booklet, you have electronegativity values. So we know that chlorine is more electronegative, which means that Cl would have a partial negative charge and hydrogen would have a partial positive charge, which is denoted as delta. Delta is partial, yeah, negative or positive, and the dipole would go from hydrogen to chlorine. I think in physics it's the other way around, don't quote me on that, but in chemistry the dipole, it shows how electron density is shifted. Yeah, so it shifted from hydrogen to chlorine. Yeah, okay, that's why I put it the line, like the arrow towards Cl. Now let's talk about, so the bond is polar if there is electronegativity difference. Now let's think, when would the molecule be polar? So the molecule is polar when both of these conditions are true. First, the molecule has polar bonds, and second is that the molecule has such a shape that the dipoles do not cancel each other out. If you know vectors from math, the dipoles, you can treat them as vectors. So if you add those vectors and you end up with 0, that's a non-polar molecule. If it's not 0, that's polar. If you have no idea what vectors are, well, just think about the shape. Yeah, so if the molecule has polar bonds and the shape is not symmetrical, basically, then the molecule would be polar. Another way, but this would only work for SL students. For HL, most of the time. So another way to find out whether a molecule is polar, I can tell you, but never use this as an explanation. Okay, that's a secret. That's like a secret way to find out about the polarity. You will never get marks if you answer and explain. Like if they ask why is this molecule polar, and then if you explain how I will explain it now, you never get marks. Okay, so use it only for multiple choice questions. Okay, so the simple way to identify whether a molecule is polar works in 95% of cases for IB chemistry. So first, well, should I write it? So a molecule is polar if, I'll write it here. So a molecule is polar if, I'm not even writing it down as, like, I'm not typing it just in case, yeah, so that no one thinks it's an official explanation. So if side atoms are different, yeah, so for example, if you have something like C H Cl Cl Cl. That would be a polar molecule because side atoms are not the same. It has H and Cl's. It's a polar molecule. Or, doesn't have to be at the same time, a central atom has a lone pair. If the central atom has a lone pair, most likely the molecule would be polar. Not always, guys. There are exceptions, but for SL students, that works. Yeah, so for SL, if you're a SL student, you can use that. Again, as unofficial way to find out the shapes, I mean the polarity. Then if you are an HL student, I've seen a question where sometimes the side atoms were different, but they were arranged symmetrically, so the dipoles did cancel out. So for example, if you think about SF something, yeah, let's see. So if it's SCl, Cl, and then F. This molecule isn't polar because the dipoles, because the chlorines, you see, they are opposite to each other. So the dipoles, one goes there, one goes there. So the dipoles cancel out. But if you, so this molecule is non-polar. But then if you switch them around, so if for example you put F here, Cl there, so this becomes polar. Yeah, so for HL, I've seen this question. It might be a slightly more complicated for HL students, but again, it's rare. So in the majority of cases, you can also rely on this kind of quick guide to figure it out. But also square planar molecules, they do have two lone pairs, but the lone pairs are arranged in such a way that they cancel each other out. So square planar molecules wouldn't be polar as long as you have the same atoms. So again, slightly more complicated. The best way to rely like on official explanation, yeah, which is here. As long as you can understand whether the dipoles cancel or do not cancel, you'll be fine. But if you don't understand how to work with dipoles, then this, but proceed with caution, okay? If you have nothing to lose, then use this. For SL, that's totally fine. Right, well, let's see. So let's just look at a few more molecules. So BCl3, non-polar, official explanation. So okay, so let's say we have a BCl3 molecule and they ask me a question in paper 2. Explain whether BCl molecule is polar or not. Explanation, 2 marks. I say BCl3 molecule has polar bonds, but the dipoles cancel each other out, so the molecule is non-polar. If it's 3 marks, I would also say that it's trigonal planar. That's why dipoles cancel out. Yeah, and you have to say that the dipoles cancel out. If you say bonds cancel each other out, or atoms cancel each other out, or electron, like anything else except for dipoles, you lose a mark. Yeah, very strict. We are very strict. Yes, fine. That's official explanation. Yeah, so BCl3 molecule has polar bonds and trigonal planar shape, so the BCl dipoles cancel each other out. Then unofficially, well, let's quickly understand whether it's polar or non-polar. It is non-polar because boron doesn't have lone pairs and all side atoms are the same, so non-polar. But again, unofficially, yeah. Now this molecule, let's just do unofficial part, yeah. So the carbon is the central atom, side atoms are all different, so polar. NH3, well, there is a lone pair which we didn't write here because it's a shape. So NH3, central atom has a lone pair, so polar. You see this blue one, it's like the overall dipole, yeah, where it's going. Then a CHCl3, polar because side atoms are different. CCl4, non-polar because side atoms are all the same, carbon doesn't have a lone pair. And the rest, side atoms are the same, no lone pairs on the central atom, so non-polar. Yeah. And again, let's maybe one more. Let's explain why NH3 is polar based on the like official definition, yeah, official explanation. So I say NH3 molecule is polar because because NH3 has polar NH bonds and the bond dipoles do not cancel out due to trigonal pyramidal shape, for example, yeah. In BCl3, they dipoles did cancel out. I don't remember what I said. I hope I said it right. But here the dipoles cancel out due to the shape. Here the dipoles do not cancel out. due to the shape. Right. With these live streams, I cannot edit, but if I make a mistake and you let me, because I'm not rewatching that, okay? I'm not rewatching this, so if you find a mistake or if I just said something wrong, because it's been an hour and a lot of minutes and 10 minutes, just let me know. I'll make a comment. Okay. Right, next let's talk about covalent structure. So we're like halfway through. Covalent structures. Remember how for ionic substances we said that they can only be giant ionic? Well, for covalent structures, they could be either giant covalent or network covalent or simple molecular. So here you have two options, not like then, yeah. For ionic, no options, just giant ionic lattice. Network covalent structures, those you just need to memorize what they are. Yes, so if a substance is covalent, and most of the time it would be simple molecules, except if it's giant covalent. So giant covalent structures are graphite, graphene, diamond, not fullerene, silicon dioxide, and silicon. Those are the ones that you need to know. So if it's one of those, it's giant or network covalent. If it's anything else for IB, that would be simple molecular. Giant covalent, what does it mean? It means that you have a lot of atoms arranged in a huge lattice. Yeah, where you have atoms and there are covalent bonds between the atoms. If it's simple molecular, it means that you have a lot of separate molecules that are not connected with any strong bonds. Yeah, then molecules are not connected between each other with any strong covalent bonds. Yeah, so no bonds. I mean, there are bonds, we'll talk about that, but not covalent. Right. 71 minutes. Yeah, okay. Now random facts about giant covalent structures. Yeah, let's just go through them. That's what you need to know for IB, SL, and HL. That's SL. So first structure is graphite. You know it hopefully from GCSE if you did GCSE or even from MYP. So graphite. In graphite, that's how it looks. So it has carbon atoms. So the black dots are carbon atoms. So each carbon atom in graphite is bonded to three other carbon atoms by covalent bonds, and this is a giant covalent structure that consists of hexagon layers. Yes, so we form hexagons. And between atoms, covalent bonds are strong, but between layers there are no covalent bonds, and the dotted lines, they are weak intermolecular forces. So there are weak intermolecular forces between the layers and strong covalent bonds between carbon atoms within the layers. What does it mean? It means that it still has high melting and boiling point, because if you want to melt it, you have to break strong covalent bonds which require a lot of heat energy, yeah, to break. But then these forces between the layers can be broken easily, and that makes graphite soft, and it makes it a good lubricant because the layers can slide over each other. Yeah, so that makes it soft. Record it to your brain. Next bit. Then graphite, it conducts electricity. Very uncommon for covalent substances to conduct electricity. The majority of covalent substances do not conduct, because we need remember, to conduct electricity we need mobile charged particles. What are those particles here? Going back, remember each carbon atom forms three bonds with other carbons, and carbon has four valence electrons. So four in total, 3 out of 4 form covalent bonds. What happens to the last one? It is delocalized. Okay, so the fourth electron in every carbon atom gets delocalized. So we have mobile charged particles, we have delocalized electrons, which can conduct electricity. Okay, graphite, recapping. Layered structure, strong covalent bonds between carbon atoms, weak forces of attraction between layers, so it can slide, it is soft, and it conducts electricity because of the delocalized electrons. High melting and boiling point. Okay, you'll memorize it before the exam. Graphene is exactly the same. So one layer of graphite is graphene. So same explanations work, except for obviously it's not soft, yeah, because there are no layers. Diamond, almost like graphite. Yeah, I wish. So diamond, it's also carbon, but in diamond each carbon forms four bonds to other carbons, unlike graphite where it was three. So just a tiny little correction, and so much more money to pay. So each carbon is bonded to four other carbon atoms, which means that it's very hard very high melting point, yeah, and does not conduct electricity because there are no delocalized electrons there, right? No delocalized electrons, so no electrical conductivity. And you can also say that the arrangement around each carbon atom would be a tetrahedral arrangement, right? Because each carbon forms four bonds, which makes it a tetrahedral arrangement, but within a giant network covalent lattice. If you say that diamond is tetrahedral, you lose a mark. Yes, you have to make sure that you explain that it's a giant lattice. Then fullerene. Fullerene is simple covalent, but it's also an allotrope of carbon, so that's why I mentioned it here, and it's mentioned there in the syllabus as well. So fullerene is not giant enough, so it's simple covalent. It forms molecules that look like a football, and in fullerene, each carbon is bonded to three other carbons by strong covalent bonds. It forms like hexagons and pentagons on the surface, and it conducts electricity on the surface of the molecule because of that fourth electron that is delocalized. Silicon dioxide, next random fact. Silicon dioxide, again, giant covalent or network covalent structures just like in diamond, but instead of carbons we have silicon atoms, which are denoted as blue, and oxygen atoms, which are denoted as red. Again, high melting point because strong covalent bonds must be broken. It is hard, and no electrical conductivity, I think. Yeah. And they never say, actually. I'd say no, but they never say. So then also, what do they ask about? Yeah, they really like to ask about the ratio of silicon to oxygen atoms. So they say that, you see, each silicon is bonded to four oxygens, and each oxygen is bonded to two silicons to maintain that 1 to 2 ratio. Their favorite question, okay? So make sure that you know the ratio. And silicon, yeah, silicon again, just like a diamond, but instead of carbons, we have silicons in the lattice, in the giant lattice. So we have each silicon bonded to four other silicons with strong covalent bonds. So high melting point, no conductivity because of the four, because it has all four outer electrons in the bonds, not delocalized. End of random facts. And then SL part again. Continuing SL, intermolecular forces. Okay, again, everyone's favorite topic, so that's structure 2.829. Everyone's favorite. So there used to be three types of intermolecular forces we need to know. Now there are four. So intermolecular forces, what is that? So remember how we said that covalent substances could be giant network or simple covalent, so the majority would be simple covalent. And if you have, let's say, water molecules, well, how does it look? Well, you have a water molecule here, you have a water molecule there, you have a water molecule there. These are separate molecules. All right. Now, within the molecules there is covalent bonding, so the bonds between hydrogen and oxygen atoms are covalent, and they are very, very strong. So HO bonds are strong, but then there are also weak forces of attraction between the molecules. So between the molecules we have very weak, compared to covalent bonds, these are weak intermolecular forces, so weak forces of attraction between molecules, right? And the most important thing that you need to remember is that if you were to melt or boil a simple covalent substance with molecular structure, you never break the covalent bonds. You break weak intermolecular forces. So if you want to melt silicon, you are breaking these bonds, strong covalent bonds. That's why it has such a high melting point. If you're melting water, you never break HO bonds, because water and steam and water and ice, it's H2O. What do you break? You break weak intermolecular forces. That's essential. And if I told you how many marks were lost because of that, like when they confused covalent bonds and intermolecular forces, a lot of marks have been lost by people who went down before you. Right, so four types of again, we only talk about covalent substances, simple covalent, yeah, with simple molecular structure. Four types of intermolecular forces: London forces, dipole-induced dipole forces, dipole-dipole forces, or dipole permanent dipole forces, and hydrogen bonding. I think I need a break. I think we'll take a break after this, after intermolecular forces. So let's talk about them one after another. Yeah. So London forces. I will first explain how they arise. So let's say you have a jar with chlorine gas. Yeah, chlorine gas. Chlorine molecules are nonpolar, which means that they don't form dipoles, so their electron density is kind of evenly distributed. But chlorine has a positive nucleus and chlorine has electrons, which are not glued to the nucleus, right? So they can move. And even in non-polar molecules, you can somehow accidentally form a dipole. Yeah, and that dipole is called a temporary dipole. So just because the electrons are moving all the time, so it is possible that at some point of time you would have a temporary dipole with one part of the molecule being positively charged, the other one negatively charged, yeah, for some short period of time. And then once this dipole is formed, it can induce a dipole on another molecule, on a neighboring molecule, because there are molecules all over, right? So if you form a dipole, then imagine another molecule comes, and then the negative part of the molecule would repel electron shell of that other molecule, so it would form an induced dipole. And if you have billions of molecules in a jar and those dipoles popping up here and there, well, the attraction between those dipoles is London forces. Yeah. Right, so induced dipoles are temporary dipoles that appear because of the interaction of electrons and nucleus of one molecule with electrons and nucleus of another molecule, and this temporary attraction between those temporary dipoles is London forces, intermolecular forces. Now, what would affect London forces? London forces is affected by the number of electrons in the molecule, which is very logical, right, since it's electrons that are moving. So the more electrons you have, the stronger the London forces. And by the way, with London forces, we can explain the melting and boiling points of halogens. For example, if you think about F2Cl2Br2I2, I wrote them how they are in the periodic table. Yeah, so you see down the group. This is so messy. Down the group, yeah, F2Cl2Br2I2. So as you go down the group, the number of electrons increases, and so which means that London forces increase. And we are talking about the total number of electrons, not valence. Yeah, valence are the same, but the total number of electrons increases. And London forces increases, which means that more and more energy would be needed to break those London forces apart, and which means that boiling and melting point would increase, and that is reflected in their standards, well, states at room temperature. Fluorine is gas, chlorine is gas, bromine is liquid, iodine is solid. So room temperature is enough to separate fluorine and chlorine molecules, to break those London forces, to make it a gas so that the molecules are so far apart. For bromine, it's enough, the room temperature is enough to make it liquid. For iodine, it's not enough at all. Yeah, so it stays as a solid, held by London forces. Molecules held by London forces. That was London forces. Bottom line, even non-polar molecules have them, and London forces depend on the number of electrons in the molecule, or molar mass. You can think about molar mass. Next one, and this is a new one, innovation from IB. So if you have a mixture of polar and non-polar molecules, then between those you would have dipole-induced dipole forces. When they say dipole, they kind of mean permanent dipole, but it's not in the syllabus, so I just use the same terminology as they are. But think about it as a permanent dipole. So permanent dipoles would be on, well, between the permanent dipole interactions would be between molecules that are polar. Yeah, so they have dipoles. Attraction between those dipoles is permanent, but then they can also be attracted to they can induce the dipole on the non-polar molecules, and the attraction between induced dipoles of the non-polar molecules and permanent dipoles of the polar molecules, that's the dipole-induced dipole intermolecular forces. Well, so basically, if the molecule is non-polar, you can only have London forces, okay? If you have a mixture of polar and non-polar molecules, you would also have dipole-induced dipole forces on top of London. I hope that's fine. Next one. The next one is dipole-dipole forces, meaning like permanent dipole force. This force, intermolecular force, exists only between molecules with permanent dipoles, between polar molecules. Again, very straightforward. So permanent dipoles would attract each other, and the attraction between the permanent dipoles is your intermolecular force. Yeah. So what's important here? It's important that if you have two molecules of approximately equal size, but one is polar, another is non-polar, then the one that is polar would have overall stronger intermolecular forces. What do I mean? Let's say we're comparing, well, for example, what can we compare? Let's check. We can compare F2 and HCl. If you think about the strength of intermolecular forces between H2 molecules and then separately between HCl molecule, which molecules would have stronger intermolecular force? Well, F2 is non-polar molecule. HCl is polar, right? But they have approximately equal number of electrons because F has 9 electrons in total, so 18 electrons. HCl has 17 plus 1, so also 18 electrons. So the fact that they have approximately equal number of electrons mean that they have approximately equal strength of London forces. So London forces are sort of the same. But then HCl is polar, which means that it has dipole-dipole forces on top of London, which means that HCl intermolecular forces overall are stronger, so it would have a higher melting and boiling point. Yeah, right. There are tricky questions sometimes. Sometimes they would give you molecules of a completely different size. For example, they could give you, I don't know, C6H6 molecule, and they can give you well, maybe what HF molecule, yeah, or NH3 molecule. HF, it has like, let's say HCl, yeah, although I'm not sure which one would have a higher, well, for example, yeah, and they would tell you that benzene C6H6 has a higher melting point than HCl. Explain why. And then here everyone makes a mistake. So they say that HCl has dipole-dipole forces and London forces. Benzene only has London forces. So you see the conclusion would have been different. So if you explain it like that, that HCl has dipole-dipole forces, which are like stronger or they are on top of London forces, then it would appear that HCl must have a higher melting point, which it doesn't. Yeah, I hope it doesn't, but like maybe the example is wrong. But C6H6, even though it's non-polar and only has London forces, it could still have a higher melting point because the sum of intermolecular forces in C6H6 is higher than the sum of intermolecular forces of HCl. So the London forces in between C6H6, it would overpower the London and dipole-dipole in HCl. Yeah, there's no way you can predict it, and even that when I was trying to come up with the example, I'm not sure that's the correct example, but in the question they would tell you that molecule A has higher melting or boiling point than molecule B, and if molecule A happens to be non-polar, well, then that's it. You don't you know that it has a higher melting point, right? Then you know that its sum of intermolecular forces must be stronger, and then you just say, well, okay, London forces are greater. Yeah, so don't try to overpower what's in the question. If they tell you that molecule A has a higher melting point, regardless of whether it's polar or non-polar, it means that intermolecular forces there are stronger. Yes, okay, and especially in recent years they had these questions. And the final, very final intermolecular force is hydrogen bonding. That's everyone's favorite. That's not a joke. Everyone is happy when they see that. Okay, so hydrogen bonding is a special type of intermolecular force. It's like essentially just like dipole-dipole, but a very strong dipole-dipole intermolecular force. So it appears between molecules which have a hydrogen atom connected to a very electronegative atom that retains its lone pair of electrons. Yeah, in practice it must be NO or F, and the NO or F, they must have a lone pair. So for example, you would have hydrogen bonding between water molecules. Why? Because there is a hydrogen bonded to oxygen, and oxygen it has a lone pair. HF would have hydrogen bonding between molecules because there is an H bonded to fluorine, and fluorine has a lone pair. Same for NH3, but for example, NH4 plus would not have hydrogen bonding because nitrogen doesn't have a lone pair. Yes, so no hydrogen bonding there. Yes, but essentially, yes, if you just have H bonded to NO or F, that would have hydrogen bonding. Right, let's see. So when we draw hydrogen bonding, we have to make sure that the bond angle OHO or um, FHF or NHN. Yeah, so the hydrogen bonding, like the bond angle between where H is in the middle, basically. Yeah, so this angle, it must be 180 degrees. I don't know why they're very picky about it, but that's how you're supposed to write it. So basically, if you draw it like this, yeah, you lose a mark because this is bent. So you're not allowed to draw hydrogen bonding as a bent thing. Yeah, must be straight. And then intermolecular forces and solubility. All SL, guys. Yeah, that's all SL. So in general, we can say that substances that have similar intermolecular forces would dissolve well in each other. For example, hexane only has London forces, so it would dissolve well in pentane, which also only has London forces, but it would not dissolve in water, which has hydrogen bonding. Yeah, and then ethanol, it can form hydrogen bonding. It would dissolve well in water that can also form hydrogen bonding. So like dissolves like. Of course, if you if you take a huge alcohol with strong London forces, then London forces would kind of overpower. But for small alcohols, that works. Yeah. So in general, if for some reason they ask you to explain solubility, it is in the syllabus, but there are not many questions on that. So like dissolves like. Yeah. So substances with similar intermolecular forces would be dissolved well in substances with similar intermolecular forces. Now, I have this flow chart which no one likes, and I don't even know should I talk about it or should I skip it. I will maybe talk about that. Yeah, so this is a flow chart. Maybe someone will find it useful. I don't know. Let's try. So, so this is a flow chart that allows you to understand how to explain comparison of melting and boiling points of substances with different structures. So the first part of the flow chart is how to compare and explain melting and boiling points for substances with molecular structure. Yeah, so if you have simple molecular substance and you need to explain, for example, why the melting point is high, why is it low, or compare. How do we do it? So first we start off by figuring out, is the molecule polar or non-polar? Well, let's say, how do we explain, for example, a low melting point of CO2? Yeah, let's say we're explaining the melting point of CO2. It's a simple molecular substance, so this flow chart works. First question, is it polar? No, not polar. How do you know it's not polar? We talked about that, yeah, before in the first hour. Non-polar, which means automatically that it has only London forces and so low energy is needed to overcome them. Yeah, that's it. If depends on the number of electrons, though. The more electrons, the stronger London forces. For example, if we were to compare the boiling point or melting point of F2 and Cl2, are they polar? No. So it means that they both have weak London forces between molecules, but chlorine has more electrons, so it has stronger London forces, so more energy is needed to overcome London forces between chlorine molecules than between F2 molecules. Okay, now let's explain low melting point, for example, for I don't know, let's say HCl. HCl, is it polar? Yes. Does it have atoms bonded, H atoms bonded to NO or F with a lone pair? No. Which means that this molecule has London and dipole-dipole intermolecular forces, and usually the total IMF is for HCl would be higher than for other molecules with similar intermolecular force. Yeah. Okay. Now let's find out the melting point, like how do we explain the melting point for HF? Is it polar? Yes. Does it have hydrogen bonded to NO or F? Yes. Which means that it has London dipole-dipole and hydrogen bonds. And I, by the way, forgot to tell you a very important thing, that hydrogen bonding is the strongest out of the three. Yeah, out of the four. Yes, so hydrogen bonds are the strongest, so need the most energy to be broken. Yeah, so like every molecule I identify from this by this flow chart, and the flow chart would tell you which intermolecular forces are there. Now let's do the comparison. Let's compare the melting point and boiling point of for example, Cl2 and, well, I don't know, let's do something else. Let's do H2O. Yeah, let's do H2O. So let's compare the melting and boiling point. So you first have to identify the intermolecular forces between Cl. Well, the first thing that you do is you understand that it's simple molecular. Yeah, that's why you use this flow chart. Then Cl2, is it polar? No, which means that Cl2 has weak intermolecular forces between London forces between molecules. Now that's your first mark. Second mark, water, is it polar? Yes. Does it have H bonded to NO or F? Yes. So this one. So water has London dipole and hydrogen bonds. Hydrogen bonds are the strongest. Yes, so we identified intermolecular forces between Cl2 and H2O. That's 1 or 2 marks. And then you compare them. You say hydrogen bonds are stronger than London forces, so more energy is needed to overcome them. That's how you explain it. Yeah. Now let's compare, for example, what can we compare? Let's compare HCl and H2. Yeah, okay. HCl, let's do HCl. Is it polar? Yes. Does it have NO or F bonded to hydrogen? No. So HCl ends up here. The molecule has London and dipole intermolecular forces. Your first mark. Hydrogen, is it polar? No, which means that it only has London forces, so hydrogen is here. Yeah, so HCl ended up here, hydrogen ended up here. So that's your second mark. You stated intermolecular forces for HCl and H2, then you compare them. HCl has a stronger overall intermolecular forces, so higher melting and boiling point. More energy is needed to overcome London and dipole forces between HCl than London forces between H2. Well, you get the idea, right? Of course, this needs practice, and hopefully I will make some bonding practice. That's when you compare molecular structures. Now, if you compare substances with completely different structures, for example, if you compare ionic and covalent substances, yeah. So how do we do it? Well, let's compare, for example, NaCl melting point and HCl boiling point. Let's use the flow chart. So I start with NaCl. Is it ionic or covalent? It's ionic. Why? Because it has metal bonded to non-metal. Yeah, so NaCl ends up here. And which means that I have to say that it has high melting and boiling point because of the strong electrostatic attraction between oppositely charged ions, which needs a lot of heat energy to overcome. Yeah. Now HCl. Oh my god, I need to remove this circle to some other point. HCl. Okay. Is it covalent? Yes, because it's non-metal and non-metal. Is it network covalent or simple molecular? It is simple. Network are only these guys, yeah. It's not one of those. So it's simple molecular, which means that it has low melting and boiling point because there are weak forces of attraction between the molecules. So low energy is needed to overcome them. And then, so HCl ends up here. So using this chart, the two compared substances, you assign them to the correct column. Yes, so NaCl is anionic, so you say this phrase. HCl is covalent, so you say that phrase. And then you just compare the forces that you need to break. So NaCl needs more energy to overcome ionic bonds compared to low energy needed to overcome weak intermolecular forces. That's it, yeah. And when you're comparing between classes, you don't really have to go into the details what intermolecular forces chlorine has, because you should only do that when you're comparing simple molecular substances between each other, yeah, but not among the classes. Fine. Let's compare, for example, let's say explain why silicon has a higher melting point than NaCl again. Well, let's do something else. Than HBr. Yeah. So explain why silicon has a higher melting and boiling point than HBr. Let's talk about silicon. Is it covalent? Yes. Is it network covalent? Yes, that's like one of the things that we need to know. Since it's covalent and giant covalent, we say that it needs a lot of energy to overcome strong covalent bonds. Yeah, so when we're melting, we're breaking strong covalent bonds. A lot of energy is needed. That's your first mark. Then you talk about HBr. Is it ionic or covalent? Covalent. Is it giant network or molecular? It is molecular. So we say that it has low melting and boiling point because there are weak forces of attraction between molecules. And then you compare, yes, you say more energy is needed to break strong covalent bonds compared to weak intermolecular forces between HBr. Yeah, that's it. So basically the bottom line, if you are melting ionic substance or boiling, you're breaking ionic bonds. Yeah. If you're melting network covalent substance, you're breaking covalent bonds. Well, here I would say attraction between oppositely charged ions. Then for network covalent, you're breaking covalent bonds. For molecular compounds or substances, you're breaking intermolecular forces. Yeah, weak forces of attraction between molecules, weak IMF. That's it. That's how you can approach those questions. 3 marks usually, 2 to 3 marks. Right, let's see. So we have 9 pages left. I think it's a good time for a short break, and then I hope no more than 30 minutes. Okay, let's take a break. I'll be back in 5 minutes. Okay, people, I'm back. Buckle up, we're going to finish this today. So, we continue. So, we finished with the melting and boiling points. Next, paper chromatography. Structure 2SL. Was it in structure 1SL? Yes, it was. Is it in structure 2? Yes, it is. Why? I have no idea. It's just the I'm just following the syllabus. Okay, that's not a question for me. I'll explain it real quick. So, paper chromatography, or actually, should I? Yes, let's do it real quick. So, paper chromatography, structure 2.2.10, is used to separate mixtures of soluble substances. You take a chromatography paper, draw a pencil line as your baseline, place your dyes, the mixture of dyes, yeah, for example, ink or plant dyes, here on the baseline. uh, Immerse this into the solvent. The solvent will move up, and depending on how well your components of your mixture are soluble in the solvent and how well they stick to the paper, they would travel to a different distance. Yeah, so the solvent would take the mixture components up with it, and you will end up with something like that. That would be a chromatogram. For example, let's say you had a brown ink here, and you see that it's separated into three spots, so it consisted of three different dyes: red, yellow, and blue. And then also you could run it to, like, for example, here, they didn't actually show. Yeah, so if it's not dyes, if it's something like mixture of amino acids, you could also run controls together with your sample. So you place your sample here, your different amino acids there, and then using the you can compare. Yeah, so if the spot traveled to the same distance as your amino acid, you know which amino acid it was. Yeah, very easy to compare the amino acids, or like to compare to identify the substances when you run controls together with your sample. Why pencil line? I explained in structure 1, because it will not be washed off together with the solution. Yeah, like when solution moves up. Then you can calculate RF value, which is distance traveled by the substance from the beginning, from the baseline to the center of the spot, divided by the distance traveled by the solvent. That's your solvent front. You have to mark where the solvent has stopped. Fine, we explained that in structure 1. If you want more details, you go to structure 1. Next one, HL part. SL students can have another break. HL students cannot. Sorry. So resonance structures. Going back to bonding, yeah. So going back to bonding, let's talk about resonance structures. So remember how we drew U structures, and remember that at some point we had to place double bonds somewhere. Yeah, like NO3 minus, we had that example. Remember? Yeah, it rings a bell. Okay, NO3 minus, for example, we had to put the double bond from any oxygen. Same with CO3 2 minus, for example. Yeah, so that's our CO3 2 minus. We have to draw a double bond to to follow the Lewis structures rule, and you can draw it from different places. Yeah, so you can draw it from this oxygen, from that oxygen, or from that oxygen, and all of these possible structures are called resonance structures. Okay, so the resonance structures occur when you have a Lewis structure and you have to place a double bond, and you can place it to different positions. Resonance structures. Yeah, fine, good. And when resonance structures can be drawn, so if you could place that double bond to different positions, then it means that the the electrons from the double bond, the pi electrons, would be delocalized between the atoms. So in fact, the CO3 2 minus would not exist as these three different structures, but instead of electrons being only between one carbon and one oxygen, those electrons would be delocalized. So these resonance structures automatically mean electron delocalization, and we can write it down as like one line and the dotted line. Yeah, so all the places where you can put that double bond, you draw as, instead of a double bond, you put the one line and the dotted line. Yeah, so I could put the double bond here, here, or there. That's why I have the dotted lines to these three oxygens. And it's important when you draw resonance structures, if they ask you to draw resonance structures, you have to write it as a Lewis structure. So you have to show all the lone pairs on the side atoms and the central atom if there are any. But if they ask you to draw the delocalized structure, no lone pairs are there, right? Because how would you know where they are? Everything is delocalized. You cannot violate the octet. So no lone pairs on side atoms when you draw delocalized structures. And for the delocalization, what do we need to know? We need to know that if the if you have a delocalized structure, then the bond length would be somewhere in between single and double. Yeah. So for example, these bonds in CO, they first of all they all have the same length. Yeah. They are not like single and double. Remember we said that single bonds are the longest, double bonds are shorter. They're shorter than single. Well, these ones would have the same length, and the length would be in between single and double, so it would be longer than double but shorter than single. Yeah, that's the sign of delocalization. That's actually the proof that the substance has delocalized structure. And again, that's HL, our favorite benzene. Benzene. A lot of benzene was excluded from the syllabus for some reason, although I don't know. I think it's an important part of chemistry, like, high school chemistry, but still. So there is not much benzene now, but still, you need to know the structure. So you need to know that this is the Kekulé structure, or the old structure of how benzene was thought to exist. Yeah, so they thought that there are carbons, right? We haven't done organic yet, but I hope you do realize that. So this is like a skeletal formula. So there are carbons here, yeah, and there are H's over there. So it's C6H6. Yeah, there are carbons, and this is the old structure. So essentially, they thought that in benzene we had three single bonds between carbons and three double bonds between carbons. Then it was proved experimentally that benzene, in fact, instead of having single and double bonds, it has a delocalized structure, and this is the formula that you're used to. So benzene is written with a circle, like a circle inside, which denotes delocalization. So they say that now instead of having localized double bonds between certain carbons, we have delocalized. So these electrons are jumping around all the carbons in the p orbitals. And we need to know the evidence of delocalized structure. So the first evidence is that if you really look at the bond length in benzene with X-ray, for example, benzene has all bonds would have the same length. Okay, so in benzene all bonds are the same length. You know what? I feel like my screen could be larger. Yeah. Okay, that's better. We're 2 hours in, and that's what I realized just now. All right, I hope it didn't interfere. Right, so all bonds in benzene are the same length. Then let's talk about this one. So compounds with carbon-carbon double bonds undergo addition reactions, like alkenes, for example, but benzene does not. Alkenes cannot undergo addition reactions, or at least not easily, as alkenes do, but instead it undergoes substitution reactions, which is another proof that benzene does not have double bonds. And the last one, and the most confusing, evidence I will explain using a diagram. Yeah, so it says that when cyclohexene reacts with hydrogen, 120 kilojoules of energy is given out, but when benzene reacts with hydrogen, less energy is released. What does that mean? Well, it's a proof again that benzene has delocalized structure. Let's look at this in more detail. So imagine we have cyclohexene. That's a real molecule. You can, maybe not you, but someone in the lab can order it, so you can buy it. Cyclohexene, a real molecule. If you add hydrogen, there is an experimental enthalpy change of this reaction, which is negative 120 kilojoules per mole. Experimental fact. Okay, let me actually calculate. I again forgot the energy of benzene. Yeah, I think it's that. Right, so now if you were to have benzene, which has three double bonds, so it would need three hydrogen. What would be the enthalpy change of this reaction that you expect? Well, 3 times negative 120, right? Because you just have three different double bonds to hydrogenate, so to add hydrogen. So the predicted value for this reaction would be negative 360. I hope that's okay, right? Because this is predicted because this substance doesn't exist. But if it existed, so if we took this substance, if benzene was like that, we would take benzene and get that enthalpy change for that reaction because it's essentially the same as hydrogenating 3 double bonds. That's predicted. And now if you take a real benzene and try to do this reaction, then the experimental enthalpy change would not be negative 360, but it would be negative 208. I should have researched this number. I don't remember it from the top of my head, but it's something like that. Yeah, so it's less exothermic than negative 360, but don't quote me on that one. You can check. You don't need to know the number, obviously. And what does it tell you? Well, again, it's a proof that benzene does not have 3 double bonds, because if it did, it would have the minus 360 enthalpy change for this reaction. What else does it show us? It shows us that benzene with delocalization is more stable than this one, than cyclohexa 135 triene or whatever that is. Yeah, so then it's more stable than this imaginary structure. Let's see why. So remember, if we draw, oh, this is a straight line. If we draw energy level diagram, well, energy diagram, so if we were to write down, like, to denote enthalpy change of the reaction, so if this guy, I need to practice my hexagons, although probably nothing can be done since I've been teaching for more than you are alive, I think, and still so you have to bear with that. Okay, so we have, if you go from this substance, let's say this is its energy, yeah, so that's the energy of that guy, and then I would put the product here. Yeah, so this is the reaction. From this to this is negative 360, so enthalpy change is negative 360 kilojoules per mole. Alright, but then if I were to write on the same diagram, if I were to write benzene plus hydrogen go into that guy, what would it be? I have to put it below, right? Why do I have to put it below? Because the enthalpy change is negative 208 or whatever that is. Again, yeah, you don't quote me on that. Kilojoules. So to make it work, because the product is the same, I have to place benzene with the ring below that thing. And what does it mean? So the substances that are lower on this diagram are more stable. So this is the most stable out of those, yeah? But if you compare the stability of this one and this one, the benzene with the ring is more stable because it has lower potential energy. Yeah, okay. That's the proof, yeah? That's just the explanation for this weird second point. Okay, digested. Next, the next bit is formal charges. Again, HL. SL people are still on a break. Formal charges. Formal charges can be used to select the most appropriate or the most stable U structure for a molecule or ion. I've seen different ways to calculate it. I think the most robust way is to just use the formula. Yeah, just memorize the formula. So formal charge of an atom equals to the number of valence electrons minus half the number of bonding electrons minus the number of non-bonding electrons. And the preferred U structure would be the one where the formal charges on individual atoms are closest to zero. Let's compare, for example, this Leu structure with that Leu structure and decide which one is more stable. Well, let's do this using the formula. So these two oxygens are the same, so I can just calculate formal charge on both oxygens in the same way. So number of valence electrons for oxygen is 6. From the periodic table, remember, group 16, 6 valence electrons, minus half the number of bonding electrons. Oxygen has 1, 2, 3, 4. Each line is 2 electrons, so times 4 minus non-bonding. 1, 2, 3, 4. 6 minus 2 minus 4 is 0. Okay, the charge is 0. Then formal charge on carbon. Valence electrons 4 minus half times bonding electrons 1, 2, 3, 4, 5, 6, 7, 8. No non-bonding, 0. Yeah. Also, you can use the fact that the sum of the formal charges equals to the sum to the charge on the ion or molecule if it's zero. Yes. So in this case, CO2 has zero charge because it's a molecule. So I know that carbon has to be zero because overall it must be zero. Fine. This is pretty stable. Everything is yours. Let's check this structure because this structure is also kind of valid because you see no octet rules are violated. Every atom has an octet, so could be fine. But let's check the formal charges. So formal charge on this oxygen. Number of valence electrons 6 minus half the bonding electrons 1, 2, 3, 4, 5, 6 minus non-bonding 1, 2, which is 6 minus 3 minus 5 plus 1. Yeah. Formal charge on carbon. Number of valence electrons is 4 minus half times bonding electrons 1, 2, 3, 4, 5, 6, 7, 8. 0 non-bonding, so 4 minus 4 is 0. And then this oxygen must be negative 1 because I know that the sum of the formal charges must be 0. So you see, we have calculated formal charges, and the Lewis structure that is preferred is this one because the individual formal charges are closest to 0 in the first one. Done. Next, HL, sigma and pi bonds. Sigma bonds formed by head-on overlap of atomic orbitals. Pi bonds formed by lateral or sideways overlap of p orbitals. Okay, that's how you write them down. So this is a head-on overlap. Yeah, so this is the hybridized orbitals. We'll talk about them in a second. This is the overlap of hybridized orbital with an s orbital. So this is like this overlap is a sigma bond, head-on. Yeah. For pi bonds, it's the sideways overlap. So pi orbitals and p orbitals. P orbitals are dumbbell shaped, and the overlap above and below the plane, it's the pi bond. Yeah, so just two types of bonding. Now, whenever you have to make sure that you know how to draw them. Yeah, just practice a little bit how to draw them, and usually one way to draw sigma bond, it's totally fine. Yeah, you don't have to know all the ways to draw them. Now, if you have a single bond, it is always a sigma bond. If it's a double bond, there would be one sigma, one pi. If it's a triple bond, there would be one sigma and two pi. So there is always one sigma and a different amount of pi bonds. For example, in this one, what do we have? We have 1, 2, 3, 4, 5 sigma bonds and 2 pi bonds. Yeah, so just draw the structure. If they ask you to find out the number of sigma and pi bonds, make sure you draw the structures correctly. And all single bonds are sigma, and double bonds 1 sigma 1 pi, and triple bond 1 sigma 2 pi. Remember, lone pairs are not counted because they're not bonding. Now the concept of hybridization, that's a bit of a confusing one, but let's try to figure it out. So hybridization, it's the mixing of atomic orbitals. Whatever that means, the definition is 1 mark. Then what do we mean by mixing of atomic orbitals? Well, imagine you have, let's say, a carbon atom or whatever atom. So let's say we have a carbon atom in an excited state. Excited because we know how, for carbon, for example, if you write down electronic configuration, it would be 2s2, 2p2, yeah? But when it forms a bond, it becomes 2s1, 2p3. That's excited state. Just even without thinking about that, yeah? So let's say we have an s orbital with an electron and 3 p orbitals with 3 electrons. We know that s subshell is lower in energy than p subshell. So if you draw energy up, s orbital would have a lower energy than p orbitals. And that's the shape. Yes, so s is spherical, p is dumbbell shaped. It was in structure 1. Now, during the hybridization, s and p orbitals would align themselves in energy. Yeah, so for example, you see what happened here. S orbital, it moved a little bit up. Yeah, so now it's like a bit higher than it was before. And these p orbitals, they moved a little bit down. So now they have some intermediate energy. Yeah, so they mix themselves in energy. So like they align themselves in energies in such a way that the energy is somewhat in between in between S and P energy of the original orbitals. And this particular type of hybridization, it's called sp3 hybridization. Why? Well, because you're mixing one s orbital and 3 p orbitals, so s1 p3. sp3 hybridization. And they not only mix in energy, they also kind of mix in shape. So when they hybridize, the shape becomes like a skewed dumbbell shaped. Yes, it's something in between spherical and dumbbell shaped. So the shape changes, and when I talked about sigma bonds, you see this is the overlap of hybridized orbitals. Yeah, okay, I hope that's fine. Now, if so, we've in sp3 hybridizations we have four sp3 hybridized orbitals. Now, you could have sp2 hybridization. In that case, one s orbital and two p orbitals would be mixed in energy. So you get three sp2 hybridized orbitals, and one p orbital would left unhybridized at its own energy. Yeah, so these would form sigma bonds, and this one would form pi bond. Yeah, so unhybridized p orbital would form a pi bond with another atom. Good, good. And also you can have sp hybridization, so these two would equalize in energy. Yeah, so they form two sp hybrids that would form sigma bonds, and two p orbitals would be left unhybridized with their own energy. Yeah, so this sp hybridized atom would be able to form two pi bonds. Fine. Okay, I hope that's okay. Uh, Usually in the questions, they would not ask you to explain hybridization. I've seen it a couple of times, not too many times, and it was this one. So you just had to show that s orbital and p orbitals like occupy some intermediate energy. But it is in the syllabus, so I would still learn that. But most of the questions would be to just predict hybridization of a central atom in a molecule. So how do we identify hybridization? Easy recipe. So to find out the hybridization of an atom, what we need to do, we just need to find out like you have a molecule, you have an atom, and they ask you what is the hybridization of nitrogen NH3. So to figure that out, you need to calculate the number of electron domains around that atom, around nitrogen, for example. So electron domain, it's either a lone pair or a single bond or a double bond or a triple bond. All of that is counted as one electron domain. Okay, so if we have two electron domains around the atom, then it's sp hybridization. If we have three electron domains, then it's sp2. Four electron domains, sp3. Very straightforward. Let's try. So if we have CH4, I draw the Lewis structure, and hybridization around carbon atom would be sp4. I mean sp3 because it has four domains. Yeah, so carbon has 1, 2, 3, 4 electron domains, so it's sp3 hybridization. Now if it's bf3, I draw the Lewis structure. They ask for hybridization around the central atom, so around boron. I have 1, 2, 3 electron domains, 3 domains, sp2 hybridization. Now let's do something like CO2. CO2, hybridization around carbon. So carbon has how many domains? 1, 2, double, remember double bond is one domain, so 2 domains is sp hybridization around carbon. That's it. Yeah, that's how you find out hybridization. That is the most common question, but explaining hybridization, it is still in the syllabus, so worth knowing, but not necessarily. Okay, done. Metallic model. How much do we have left? Metallic model, bonding continuum. Okay, not half an hour that I planned. All right, metallic bonding. SL, back to SL. SL people are back from the break, I hope. Yeah. So metals. Metals are made up of a regular lattice of positive ions surrounded by the sea of delocalized electrons, and that is everyone's favorite definition. Everyone remembers the sea of delocalized electrons, but please also remember the positive ions in the lattice, not nuclei, okay? Not nuclei. Positive ions surrounded by the sea of delocalized electrons. What does it mean? Well, that's essentially instead of atoms in a lattice, if you have a metal, it would not have atoms in the lattice, but atoms would lose their outer electrons, and those electrons would be delocalized. throughout the structure. And this arrangement leads to special properties. So metals conduct electricity in solid and molten states, both solid and molten, because they have delocalized electrons that can move through the structure and carry charge. Metals are malleable, which means that they can be bent into different shapes, and that is because ions are arranged in layers and layers can slide over each other. This is the mark scheme answer. Yeah. So make sure you know how to explain malleability. So metals can be malleable, can be bent into different shapes because you can bend them. Layers can slide over each other. Electrons are mobile, so whenever you have cation repulsion, electrons just go there and compensate for that repulsion, so nothing shatters apart. If you think about, for example, ionic substances, if you try to bend an ionic substance, you would have repulsion between cations, anions and anions. Everything will shatter, so they're brittle, they're not malleable. Yeah, here malleable. Metals have high melting and boiling points. Why? Because of the strong attraction between ions and delocalized electrons. And guess what? The more delocalized electrons you have, the larger ionic charge you have, and the smaller ionic radius you have, the higher the melting and boiling point would be. So think about attraction between, like in ionic substances, that's the same, yeah? So the larger the charge, the smaller the radius, the better the attraction. That's it. But one word of warning. Yeah, so for example, well, and say same factors affect the strength of metallic bond. Yeah, so larger charge, larger numbers of delocalized electrons, smaller radius means stronger bonding. So if you were asked to compare the melting point of sodium, magnesium, and aluminium, well, better boiling point. Yeah, let's do boiling point because melting point aluminium doesn't fully um, like destroy its metallic lattice, but let's do boiling point when everything is fallen apart. So we say that sodium has a charge of +1. Why? Because you see it's in group 1, sodium, so it has one electron in the outer shell, which it can delocalize. Magnesium group 2, so it has a charge of +2. Aluminium group 3, 13, so charge is +3. And sodium has 1 electron per atom, magnesium 2, aluminium 3. So we expect aluminium to have the highest melting or boiling point because it has the strongest attraction between the ions and delocalized electrons. Now, if they ask you to explain the trend in melting points across period 3, for example, then you have to understand that metal stops here, okay? So silicon is not metallic lattice, it's giant covalent. So you have to refer to giant covalent lattices. These guys are simple molecular. Yeah, so it's not like the boiling point or melting point increases across the period. That's completely wrong. Yeah, so we talk about metals separately, then silicon separately, and these guys separately. Fine. Next one. If we think about metals, how melting point of metals changes down the group. Well, down the group, let's say down group 2, yeah, or 1, doesn't matter. Down the group, I expect the melting point to decrease and boiling point. Why? Because radius increases, ionic charge does not change. Yeah, the group 2, for example, always has +2 charge, but and overall the charge density would decrease. Yeah, charge density is how much charge you have per unit volume. And so electrostatic attraction between delocalized electrons and ions gets weaker. Right, and there was this note about delocalized electrons in transition metals. I think that's part is HL, although I'm not sure. I think it is an HL part. And so transition metals have d electrons that are close in energy to s electrons, so they can also be delocalized, and that results in a much higher, like in a very high melting and boiling point and very good electrical conductivity of transition metals. Random fact for HL students, I told you, I it it was there. It was in my notes. Okay. And the final, not the final, 3 more pages, guys. Okay, we're almost there. Now, this is a new part of the syllabus, which is called From Models to Material. And the first thing that we need to do is to talk about bonding continuum. This triangle is from the data booklet. I think it's I'm not sure if it's exactly from IB, but I think it's something like that, something similar at least. So remember how I told you when you combine two nonmetals, that's covalent bonding. If you combine a metal and a nonmetal, that's ionic bonding. Well, that's wrong. Yeah. So ionic and covalent and metallic bonding, they form a so-called continuum. So you can say that a substance can have some ionic character and some covalent character. So let's see. Uh, to find it out, we need to find the electronegativity difference and average electronegativity in between the two atoms that are forming a bond. Yeah. For example, let's find the covalent character in NaCl. These values are electronegativity difference from the data booklet. So these they would give you. So to use this triangle, I need to find the electronegativity difference. That's what I would do. So electronegativity difference would be 3.2 minus 0.9, which is what, 2.3, right? According to my very powerful mental math, yes. And average electronegativity, for some reason it's written as sum, I will use the same symbol. It's sum over 2, yes, so that's the average. So 0.9 plus 3.2 over 2. 0.9 plus 3 over 2 is 2.05. Well, and now I have to find those numbers on the triangle. So, uh, difference 2.3. Well, approximately where? 2.3, approximately here. Yeah. And the average 2.05. Well, approximately 2. Yeah. So I go up there. So what does it show me? It shows me that the substance is mostly ionic, and then the covalent character would be 25%, ionic character 75%. They asked for covalent, so I'd say 25. Right, next bit. The next bit is alloys. Alloys are homogeneous mixtures of two or more metals or a metal with a non-metal. And examples of alloys would be steel and brass. Yeah, not sure you need to know them, just in case it is there. So alloys. Alloys are harder than metals because their regular lattice is disrupted and layers cannot slide over each other. So imagine you have a regular lattice of iron and you introduce some carbon or some other metal into it, yeah. So that other metal or other atom would have a different size, and that size, you see now this lattice is not regular, and since it is not regular, it would not be able to slide. Yeah, no sliding means no the substance isn't malleable. So addition of four ring atoms makes the metal stronger. Sometimes you don't need malleability, sometimes you want the metal to be strong. That's it. This is a mark scheme answer for why alloys are harder than metals. Next bit. The next bit again, SL, structure 2.4.4, polymers, introduction to polymers. Do not ask me why it's all of a sudden here after the bonding. I think it's because it's materials. Probably, yeah, probably that was the logic. So, polymers are large molecules built from small units called monomers. You have a large chain made out of small polymers. And now random facts about properties of plastics. Maybe you were wondering. Plastics, low weight, yeah, so they are loosely packed, so they usually are quite light. They are unreactive because they contain strong carbon-carbon single bonds, which, as we know, require a lot of energy to be broken. They are water resistant and they are strong because they have many strong covalent bonds, which makes them useful for packaging, construction, clothing, and transportation. This you know better than them. I think you can figure it out. Yeah, when can you use plastics? And then we need to learn addition polymerization of alkenes. Again, we done alkenes? No, we haven't. Have we had any introduction to organic chemistry? No, we have not. So, but it is in structure too. Right, so if we have an alkene it's an organic molecule or class of organic substances with a double bond between carbon atoms. So you have carbon-carbon double bond and something else. Yeah, each carbon has four bonds that we know from somewhere, from common sense knowledge because carbon has 4 electrons in the outer shell. Carbon always forms 4 bonds. So you have this molecule. If you want to make a, so alkenes can form polymers, addition polymers. If you need to make a polymer, what do? We take the double bond, break it, make it single, open it up on the sides. You see, I redraw that. These guys, they are just there. Nothing changes. And this thing is a repeating unit. Yeah, so that's a repeat unit of your polymer. So it would be repeated many times. And how many times? Well, n times. Yes, so if you take n molecules of your monomer, you will have the polymer with n repeat units. Example: draw a repeating unit of a polymer made out of that but2ene. Okay, so my goal is to do the same reaction. So I want to break this bond. Yeah, to break this bond, I have to rewrite it. So these are the carbons I'm interested in, the ones that are at the double bond. The first carbon has H attached and CH3. Yeah, so this CH3 attached to C and this H attached to C. And the other carbon has the same. How I do it, draw it up or down, doesn't matter. I redrew it. That's my monomer, which I don't need, by the way. Yeah, but I still redraw it because then it would be easier to draw a repeat unit. Then I break the double bond, make it single, open it up on the sides, and that's it. And the rest I keep. Just identify the correct carbons that you need. Yeah, these are the ones at the double bond. Okay, that's my repeat unit. You can put n, doesn't matter, but if you were to put n, there is this I don't know who made this rule, but basically if you draw the repeating unit with the n, you have to put the brackets, and the brackets have to intercept these lines. Again, I don't know why. It's just some convention or something. If you draw it without interception, you lose a mark. I'm just saying. Yeah, I'm just warning. So I didn't make those rules. That was addition polymerization. And next is condensation polymerization, and we are at the very last page of structure 2, and that is HL. SL students, congratulations, you're free to go. Do whatever you need to do in the summer. Right, and then for HL students, we still need to go through a condensation polymerization, but again, this doesn't really make sense because we haven't done organic chemistry yet. I just explain. So condensation polymers, you need to know how to form polyesters and polyamides. I hope you know some organic chemistry at this point, because if you don't, you can skip it and then go back later. Yeah, but unless you need it for the exam. So polyesters. Esters are organic compounds that contain an ester bond, which is this one. Yes, see a double bond OO, and you can make polyesters from a dicarboxylic acid and a diol. You can make a normal ester from a carboxylic acid and alcohol, while polyester from a dicarboxylic and a diol. So this is your dicarboxylic acid. This is like a carbon chain, yes, so CH2, 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 for example, and you have COH groups on both sides. And this is your diol. Again, this is like CH2 groups, CH2, CH2 chain, carbon chain, and you have two OH groups on the sides. So when the polyester is formed, what do you do? You remove OH from the acid, H from the alcohol. So you see this forms water. Water is gone. And this is your ester bond. So basically this part connected to this part. There it is. Yeah, that's your ester. But if you just keep it like that, if you keep these ends, it's not a repeating unit yet. To make a repeating unit, what you need to do is you have to remove the reacting pieces from both sides again. So from this side, you see I removed OH because that's the part that would react in the next step. And from the right side, I removed the H because that's the atom that would react in the next stage. And then open up the lines, intercepting the brackets. That's your polyester. Well, if you want to do it to have an example with real molecule, well, for example, you can take that benzene 1,4-dicarboxylic acid and ethane 1,2-diol. So you see what happened. We removed this group and this group and attached these parts. There they are. Yeah, that's your ester. And then you remove reactive groups on the side. So I have to remove this one, and there that's gone, right? And I removed this one. Well, H is gone from there, and that's your repeating unit. That was a polyester. Next one is polyamide. Polyamides, again, you can form it from many different things. For IB, according to the syllabus, I understand that you only need to know how to form them from a dicarboxylic acid, that's the same as before, and diamine. So again, OH is gone from a carboxylic acid, H is gone from the NH2 group. We have this and this attached. That is an amide link. Yeah, peptide maybe from biology. That's such a bad way to explain. Yeah, so we form an amide, water is gone, and then I also remove reactive groups on both sides. Would react in the next step, and that, yeah. There you go. C double bond O NH. Square brackets if needed, not necessarily. If you draw them, remember lines are intercepting. And this is a real life example of Kevlar polymer. You need to know this for A level, by the way. All the names. So OH group, OH group. Yeah, this is gone. See, H is gone from there. This is gone. One hydrogen is gone. You get an amide link, same as before, just with real molecules. Yeah, because this is just some carbon chain. Okay, guys, you did it. I did it. Congratulations. I hope there was some sound on this video. So we're finished with structure 2, SL and HL. Now I have to make some timestamps. If you have any other topics that we need to cover, you can send me a message. You wrote something in the chat, but probably I will forget about the chat. So if you just leave a comment, I will see it better. So I let you go. Next time we'll see again. We'll see how this video goes. So if you want me to continue with these lengthy live streams, you have to react. You have to like the video, subscribe, and tell your friends that I'm doing these kinds of lessons. What else? Yes, and then the next lesson probably it would be for A-level chemistry students. But again, if you want me to explain any specific topics, just message me. Right. Thank you for watching and see you next time.